So ask yourself honestly, does your data workload actually need a massive, hyper-complex distributed execution model? It's the question that kind of haunts modern data engineering. For years, we've just assumed that to process big data, we automatically need hundreds of nodes and endless layers of infrastructure. But what if that assumption is fundamentally flawed for most enterprise workloads? Welcome to today's Explainer, where we're going to challenge the default mindset of data architecture. Today, we're unpacking a really fascinating evolution in data engineering called DuckLake and its paradigm shift toward vastly simpler lakehouses. We're going to look closely at how DuckLake rethinks lakehouse architecture from the absolute ground up. By the end of this explainer, you're going to have a clear understanding of how shifting just one major architectural decision, specifically where your metadata lives, can radically transform performance, slash costs, and make your engineering teams significantly happier. Here is our roadmap for today. We'll start with the lakehouse complexity problem, explore DuckLake's relational solution, and see how it solves the notorious small file problem. Finally, we'll rethink distributed architectures and look ahead to AI and data engineering. Let's dive in.
All right, part one, the lakehouse complexity problem. Before we look at the solution, we have to validate the very real infrastructure pain points that data professionals are wrestling with right now.
Look, modern data lakehouses exist for a great reason, right? We all wanted the cheap storage of a data lake combined with the transactional reliability of a data warehouse. Technologies like Apache Iceberg and Delta Lake totally paved the way here using open formats like Parquet. But, and this is a big but, in doing so, they kind of accidentally created a massive metadata file nightmare. Traditional open formats manage the state of a table through this ever-growing hierarchy of metadata files, manifest lists, and pointers. And all of that is just sitting right next to the data in object storage. And you know as well as I do, this architectural choice creates a total domino effect. Object stores, like S3 or Google Cloud Storage, they are amazing for holding data, but they are frankly terrible at acting like relational metadata engines. If you ask the system, hey, what did this table look like 3 days ago, the engine literally has to scramble. It triggers a huge spike in API calls, adds network latency, and bogs down transaction commits. As that metadata history balloons, having to constantly traverse the object store leads to nasty write conflicts and a whole lot of maintenance headaches. It's a mess.
Which brings us to part two, DuckLake's relational solution. This is where the architecture takes a really fascinating pivot to escape that trap we just talked about.
The core idea behind DuckLake is incredibly straightforward, but the implications are absolutely massive. Instead of wrestling with a tangled web of metadata files and object storage, DuckLake flips the script. It keeps your heavy analytical Parquet files in that cheap object storage, sure, but it yanks the metadata out. It manages all that metadata entirely inside a lightning-fast relational SQL database.
So what's the actual payoff here? Well, think about it. The relationships between schemas, snapshots, and columns are highly structured. That is literally exactly what relational databases were built to handle. By moving metadata there, you get exponentially faster snapshot resolution using indexed SQL. No more crawling through object stores. You also get way lower commit overhead because, hey, you're just updating rows, not generating and uploading a dozen new files. You get tighter retry windows. And the absolute best part? Observability is built right in. You can just fire off a standard SQL query against your catalog to check table history or data distribution. It's a real game changer.
Let's move on to part three, solving the small file problem. This is that persistent operational headache that keeps data engineers up at night. In traditional setups, high-frequency microbatch writes create thousands of tiny Parquet files, and query engines just choke trying to open and read them all. DuckLake tackles this head-on with a clever mechanism called inlining. When a small insert arrives, it doesn't immediately create a new Parquet file. Actually, scratch that. It doesn't even try to. Instead, it temporarily stores those durable rows straight into the relational catalog. It uses the catalog as a buffer, accumulating those rows, and only when it hits a specific configured threshold does it flush everything into a properly sized, optimized Parquet file.
Now, you might be wondering, wait, are we just trusting our critical business data to temporary application memory? Absolutely not. These inline records fully participate in standard ACID behavior. Once a transaction is committed, it is fully durable and queryable. It doesn't matter if that data is currently sitting in the inline relational structure or if it's already been flushed out to a Parquet file. You essentially get the performance of streaming ingestion without sacrificing an ounce of data integrity. All right, part 4, rethinking a distributed architecture. It is time we address the elephant in the room when it comes to single-node query engines.
Because DuckLake leverages DuckDB, which is largely a single-node engine, people automatically assume it can't handle enterprise-scale data. But honestly, that assumption belongs to an era of slow storage and tiny memory limits. Today, modern hardware paired with highly optimized vectorized engines gives you massive single-node capacity. We're talking fast local SSDs, multi-core parallelism, and DuckDB's clever ability to spill intermediate data to disk when memory gets tight. A single machine can chew through surprisingly huge workloads. I mean, let's be real, most business queries just don't need to read an entire petabyte-scale table all at once anyway.
Now, just to be perfectly objective here, DuckLake isn't trying to completely kill off Iceberg or Delta Lake. If you're running extreme multi-petabyte processing pipelines or training global machine learning models across massive clusters, yeah, the traditional distributed ecosystem is exactly where you need to be. But DuckLake represents this really powerful alternative architectural branch. For small to medium analytical workloads, customer-facing analytics, or any environment where you prioritize minimal setup complexity and lightning-fast snapshot resolution, DuckLake offers a vastly simpler path. And this simplicity translates directly into engineering time. We all know complex distributed architectures carry hidden tolls. Teams end up spending half their week provisioning databases, fighting obscure Java versions, trying to resolve impossible package conflicts, and fixing operational failure points, the whole shebang. DuckLake's simplified setup completely reverses this ratio. By stripping away the infrastructure layers required to spin up a functioning lakehouse, your team can actually focus their engineering hours on creating real business insight, rather than just babysitting the environment. Which brings us to our final section, Part 5, AI and Data Engineering. How does all this architectural simplicity prepare us for the future? Well, we are rapidly entering the era of agentic analytics. If you point an AI agent at a sprawling, highly complex, distributed file system, it is going to struggle with the countless failure modes. But when you have a clean relational metadata catalog, that becomes a rock-solid semantic foundation. An AI agent can easily query this catalog to understand exactly which table holds customer invoices, verify business definitions, and accurately grab valid snapshots for time travel. Simplicity makes your data environment infinitely more accessible to AI. There's a really great analogy for this shift. Think about when advanced calculators were introduced. Calculators didn't eliminate mathematics, right? They just allowed people to solve much more difficult problems. AI coding agents are going to handle the routine tasks, inspecting directories, generating boilerplate SQL, documenting datasets. But this doesn't replace the engineer. It elevates us. Engineers are going to shift from fighting infrastructure to framing high-level business problems and ensuring solid data governance. Which leaves us with this final critical thought to evaluate your own systems. Are we building complex infrastructure because our workload genuinely demands it? Or just because it's what we're used to? DuckLake proves that by intelligently rethinking just one piece of the puzzle, relational metadata, we can radically simplify our systems, lower costs, and empower both our human engineers and our future AI agents. Thanks so much for joining this explainer, and I highly encourage you to test out this simpler path on your next analytical project.